Hello. Uh, so, in the first module, we will be trying to understand few important aspects about the Earth's atmosphere. So, this module will be an introduction to Earth's atmosphere. We will not look into the processes. We will try to understand the atmosphere in its whole size, and we will try to quantify various important physical parameters, how large or how small, how significant or how insignificant these parameters are. So, today we will talk about the evolution of the atmosphere. So, the atmosphere that we know today is the oxygen and nitrogen and a few other gases. We have to understand, was the atmosphere the same from the eternity, let us say since the beginning? Was the atmosphere existing in the same chemical composition, or was it different? If it was different, how did we get here? I mean, what was the atmosphere in the beginning, and what are the processes which made sure the atmosphere was today it was in these concentrations with oxygen dominant, so that life exists on this planet, right? So, we will try to give a historical perspective of the physical and chemical processes which resulted the atmosphere in a ratio of 78 to 21 between nitrogen and oxygen. So, we will start our discussion by understanding the atmosphere once again, let us say. So, I will read it out for you. The atmosphere is a cloud of gases and suspended solids extending from the Earth's surface out to many thousands of kilometers, becoming increasingly thinner with distance, but always held by the Earth's gravitational pull. The atmosphere is made up of layers surrounding the Earth that holds the air that we breathe, protects us from the outer space, and holds the moisture, gases and tiny particles. In short, let us say the atmosphere is the protective bubble that we live in. So, we live in this bubble. So, on the surface of the atmosphere is the thin layer of gases which is held by the gravitational pull of the Earth and extends nearly to, let us say, 800 or 1000 kilometers. Right. Now, how did this atmosphere came into existence? So, we should start at this point of, let us say, around 4.5 billion years ago, when the Earth formed. So, the Earth formed nearly 4.5 billion years ago. So, when the Earth formed out of the nebula of gases and dust particles, rocks, that were to become the solar system. So, this gases and dust were to become the solar system. So, Earth formed out of these gases and dust, and with time what happened is smaller objects called as planetoids accreted or came together or combined to form or to result into larger objects which are called as planets. So, Earth formed out of these planetoids. I mean, larger objects came together, agglomerated, and then it resulted into the formation of a rocky surface or rocky planet that we call as Earth. Fine. So, for reference from here onwards, let us say we need to have a reference for the time scales. Let us say we talk about today. What is today? Today is something which has an elapsed amount of time of 4.5 billion years, let us say. So, giga annum is 1 billion years, let us say. So, this age of sun is 4.6 giga annum, 4.603 giga annum. Earth is 4.543 billion years. Moon is 4.53 billion years. So, solar system that we know as today is 4.571. Solar system is the point where we have the sun, planets, and rest of the things. Known universe. The age of known universe is 13.722 billion years with a plus minus of 59 million years. And the first life form existed on this planet or originated in this planet nearly 3.85 billion years ago. Okay, so this is the reference. I mean, so now, so we are at, let us say, 4.5 billion years after the formation. Let us say we call the formation. Now, this formation, after this amount of time, we have the 78% nitrogen and 21% oxygen. So, this is the present day chemical composition. Now, so in the beginning we said it is the small objects which came together and formed what are called as planets. So, we call this as the planet. Now, our journey will start from the point of atmosphere at this beginning to this point. So, this entire discussion can be simply called as the evolution of atmosphere. Now, one thing we should keep always in mind is that the processes that I am going to explain can actually be similar to any other planet. Okay. Or to begin with, we can simply say that not just the Earth, the Venus or the Mars, the rocky planets, must all have formed in the similar way. And if the conditions were suitable, they should also have the atmosphere which is just like us. So, in this discussion, not only we will see the processes which led from here to here, or we will also see the processes which were deviated away for other planets, let us say for example Venus or Mars, okay, things like that. Okay. Now, so at the formation, immediately when the Earth formed, the process of Earth formation was complete before 4.5 billion years. Okay. At that time, what has been thought, I mean all this discussion, or the entire discussion is based on the theories. Few things have been verified by kind of experiments or measurements or observations. Few things were more acclaimed to be true. So, if you believe the fact that 4.5 billion years ago the formation of Earth has occurred already, Earth experienced a period of internal melting due to the enormous amount of heat and pressure of when the objects come together by the means of gravity. So, the gravity is the only thing which is pulling these objects together, right, forming out of nebula of gases. Due to the internal high temperatures and heat from the radioactive decay, there was a lot of heat. That means the Earth experienced a period of internal melting, internal melting. Okay. So, the dense elements, heavy elements like iron, nickel, metals sank to the core, I mean they started going deep and getting accumulated at the core of this planet. And the lighter elements, for example gases or any other lighter species, started to rise to the surface. They started occupying the surface, and the heavier element started occupying the core. That means that was the time when the core was formed. So, we know that right now today we know that the Earth's core is a molten iron core we have, which is rotating. So, right. So, this started at the very beginning when the heavier elements started going towards the core, the differential of the Earth. Okay, and the lighter elements came to the surface. So, the initial crust, I mean the crust that resulted from the lighter elements was too thin to be able to support tectonics as we know today. So, yeah. So, let us talk about the atmosphere. So, that was the formation of the rocky planet itself. Now, about the gases. Now, there are many number of theories which will give you how the atmosphere must have resulted, how the initial atmosphere, how the primordial atmosphere must have resulted. Generally, when the objects come together, and if they are started to come together by the action of gravity, then it will systematically get rid of the gases, because the gases are light and they are volatile in nature. So, they tend to go out of this agglomeration, right. So, the early atmosphere would have been similar to Sun, because the cosmos is hydrogen and helium. So, it must have, the early atmosphere must also have been similar to hydrogen and helium, just like Sun. Okay. The atmosphere of the Earth was, I mean the one contradiction here is that the atmosphere of the Earth is remarkably deficient in noble gases. This is one contradiction which gets away with the assumption. Okay. And it is assumed that the Earth formed in such a way that when the rocky objects came together, it got rid of the volatile substances by itself. So, it systematically excluded all the gases. All the volatile substances were systematically excluded in such a way. Okay. Or it may also be possible the initial atmosphere was lost as soon as the Earth formed itself. So, initial atmosphere, the primordial atmosphere was lost as the Earth formed. So, there are many aspects which support each of these theories, and let us see what the merits and demerits of each of them. Okay. Now, the loss of primordial atmosphere is a very important process which began the formation of the Earth's atmosphere. So, the gravity of the modest size Earth was not strong enough to be able to hold the gases. This is a very agreeable theory, of course. It's not a planet in its complete shape or not in its complete size. So, this Earth provided a gravity which is feeble for or in comparison to the root mean square velocity of the gas. So, the gas must have escaped. So, that means that there were large chunks of masses which came together and formed the Earth, and there was also gas, there was dust, there was a lot of dust. But this initial gravitational pull was not sufficient to be able to hold the hydrogen and helium gases or volatile substances, if there were any, and it escaped. That means that the primordial atmosphere was lost as soon as the Earth formed. The slightest idea of the formation of the planet was to be treated at the same time when the primordial atmosphere was lost. So, to support this, it appears that nearly around 30 million years after the Earth's formation, let us say 4.5 million years minus 30 million years, it was struck by a large object the size of Mars. And as a result, the origin of Moon and loss of Earth's hydrogen and helium atmosphere. So, another theory which supports the or which looks at the loss of primordial atmosphere is that after some time it was struck by a very heavenly object, and this also resulted in the formation of Moon. This is another theory, and not so acceptable theory. I mean, it is not so accepted because is that solar wind driving away all the primordial atmosphere, which is not accepted actually, because the solar wind also comes with the fact that nearly 4.5 million years ago, sun was not as active or as energetic as we see today, and the solar wind must not be so powerful enough to drive away the hydrogen and helium that exist, or the primordial atmosphere that we call away from the Earth. It's not physically feasible. Okay, so this is just an artistic impression of the Earth being struck and then resulting into the Moon and loss of the primordial atmosphere. Okay. Now, it is accepted that this debris must have resulted in the formation of Moon. Okay, that is not a point of discussion now. Now, what happened is the surface of the Earth was very hot that time, and due to the coming together of large objects, what happened is a lot of volatile substance was trapped between these large objects. Okay, so these voids that you see, it was assumed that there was a lot of volatile substances which were trapped in these areas. Volatile substances or gases, anything. There was a lot of volatile substance which was trapped in this. Okay, and since the temperatures were hot, it so happened that it resulted into large volcanic eruptions. The surface of the Earth during this period was extremely hot with numerous amounts of volcanoes. So, this volatile substances being heated to very large temperatures inside have to find a way out. So, this led to the formation of volcanic eruptions. So, the Earth was under near constant, and at the same time Earth was also under nearly constant bombardment of objects of varying sizes for nearly 500 million years. So, as a result of all these things, so volcanic eruptions happened. They released a lot of gases into the atmosphere. Slowly, the Earth started to cool as a result of these volcanic eruptions and the resulting rains. Earth started to cool and a secondary atmosphere started to form. Okay. Now, so if now the point is you have a primordial atmosphere which was existing at the same amount of time when the Earth formed. Now, we have enough reasons to believe that this primordial atmosphere was lost. I mean, this is not to be discussed. Then after the primordial atmosphere, then you talk about the volatile substances which are trapped between the planetoids, let us say, and these volatile substances resulted into volcanic eruptions, and this volcanic eruptions resulted in the formation of rains and formed what is called as the secondary atmosphere. secondary atmosphere. Okay. So, new atmosphere was established by the outgassing of volcanoes, rains, the mixture of gases was probably similar to the volcanic eruptions, the chemical composition of volcanic eruptions is pretty much known. So, we can safely assume that this chemical composition must also have been same at that time, which is nearly 80% of water vapor. So, it is mainly the water and carbon dioxide and nitrogen and small amounts of things like hydrogen sulfide, methane, ammonia, hydrochloric acid and other trace gases. And one important aspect that you have to understand here is that, let us say here there is no free oxygen that is available. So, the volcanic eruptions have released a lot of water vapor into the atmosphere, lot of water vapor. Let us not talk about condensation. If this water vapor condenses, then you will get water. Let us go step by step. So, the volcanic eruptions have provided a lot of water vapor, nitrogen, carbon dioxide into the atmosphere. So, now the secondary atmosphere is mainly this. Secondary atmosphere is just the water vapor, carbon dioxide and nitrogen. Okay. Now, what happened after that? So, what happened after that? So, at the secondary atmosphere virtually there is no trace of oxygen, right. Now, what I am doing is I am trying to build up a connection between this atmosphere which you call as a secondary atmosphere to an atmosphere which is rich in N2 and O, that is it. Now, my idea is the primordial atmosphere which is hydrogen and helium. So, I have to get from here to here. So, now I have introduced a secondary atmosphere which is mainly dominant in H2O and CO2, that is it, a very small percentage of N2. Now, you should always remember this N2 which is percent, let us say which is, let us take it to be 1% to be modest, let us say. This N2 which is 1% should be, we should get from this 1% to 78% N2. So, we are very far, the journey is very long, because so the atmosphere must have been just water and other CO2 and N2 things like that, and from here we have to travel all the way when we get 78% N2. Okay, let us see how we get there. The secondary atmosphere, there was no trace of oxygen, there was no trace of free oxygen in the secondary atmosphere. Okay. Thus, if there is no oxygen, there is no ozone layer, of course, and that means that ultraviolet radiation must have flooded the Earth's surface just like anything. So, ultraviolet radiation is consumed by ozone actually. Okay. So, for the formation, for the breaking, both of them, ultraviolet radiation comes handy for the ozone. So, when there is no oxygen itself, there is no point we can expect ozone to be present. So, there is no ozone layer. So, ultraviolet radiation flooded the Earth's surface with a huge influx of water vapor and the cooling of the planet. Clouds of oceans, clouds and Earth's oceans formed. So, I said let us not talk about the condensation, now we talk about the condensation. So, there is a lot of water vapor, and if there is cooling, this water vapor will condense and result in the formation of water, liquid water. Yeah. So, at that time the sun was, now one more important aspect which kind of competes with this understanding is that at that time the sun was about 30% weaker than today, exactly like 4.4 billion years ago the sun must have been not as bright as it is today. So, 30% weaker. So, why did not we freeze over? It is naturally that, so we at this time we are at the temperature of nearly let us say 35 degrees average temperature, but so had the sun been 30% weaker than today, the temperatures must have been very low, right, naturally. So, it must be in a condition that water must have frozen or it resulted in ice crystals, but it is also one important aspect which counters this is that the apparent reason, but that there is so much of CO2. So, CO2 is able to hold the heat radiation and keep the planet warm. So, this additional amount of CO2 that we had in the beginning must have been able to keep an average temperature of this Earth at a level when the water does not just freeze and result into a ice planet. And so, this is this CO2 must have given a very strong greenhouse effect. Okay. Now, so at the 4.2 billion years ago, let us say, when the secondary atmosphere was getting cooled, So, secondary atmosphere getting cooled means the water vapor getting condensed or forming into the liquid water resulted in the condensation, and after several hundred million years of rain. So, it must have this condensation happened over several hundred million years of time and resulted in the formation of the great oceans. So, okay, it is okay. So, still water has not dissociated. I mean, it's the molecule is still the water molecule. So, there is still no direct trace of oxygen. So, it is still the H2O and CO2 which are dominant in this atmosphere, the secondary atmosphere. In order to understand how this atmosphere transformed into a state from this to N2 and O, we need to understand, we need to bring something else. Atmosphere transformed into the state that we see today, we need to consider the earth as a complete system. That means that in order to understand how this chemical composition changed from here to here, we do not just talk about the atmosphere, we talk about the earth system itself, we just do not talk about the atmosphere. No. So, just discussion about atmosphere is not sufficient. Let us say what else we need. We need the complete earth system to understand this. Earth system comprises of 4 different subsystems, let us say. The biosphere involves, comprises all the living matter, all life or organic matter. Lithosphere is all the crust which is inorganic. Hydrosphere is all the water, and the atmosphere which is the gaseous envelope that we see. So, now we want to understand how things are changing in atmosphere. So, my point is, let us not just talk about atmosphere. These 4 regions are intercoupled with each other. If you want to understand something that is happening here, we better couple this with all other 3. Okay. Then we will see how the oxygen has resulted. Ultimately, we have to understand oxygen, or how oxygen has how oxygen came into existence. One important aspect is oxygen is life and life is oxygen. So, these 2 are intercoupled. We have to get to the point where how oxygen has resulted, and then we will see how life has added to the inclusion of oxygen into the atmosphere. Okay, so, the total mass of volatile substances in this system, in the earth system that we see, in this total mass of volatile substances in this earth system is nearly 0.025% of the mass of earth. That means, the total mass of gas, liquid, whatever it is, the volatile substance is very, very small in comparison to the mass of earth, very, very small. Okay. And of this very, very small percentage, the atmosphere, the gaseous envelope represents only 1/300th of the entire mass of hydrosphere. Okay. So, all the secondary atmosphere has resulted into oceans, yes, all the secondary atmosphere is the H2O. All of the water vapor that was thrown into the atmosphere by the volcanic eruptions have resulted into the formation of the great oceans. Okay, so, water is there. So, oxygen is also there in the oceans itself, but is with the hydrogen, I mean in the form of water vapor, water. Okay. Now, the present day inventory, I mean today, let us say today, if you see how the hydrosphere is existing in different forms, you see that the hydrosphere is existing as at 97% in the oceans. This is the inventory of hydrosphere, how much of water is there everywhere. Ice in the form of ice has 2.5%, fresh water 0.6%, fresh water, lakes and rivers 0.02%, atmosphere as water vapor is 0.02%. So, this is a very small number that you see here. Okay. So, atmosphere, so that means that of the total hydrosphere, atmosphere has the ability to hold very small amounts of water vapor. Okay. Now, just to make sure, so if you want to see, let us say if the volcanic eruptions have resulted in the formation of liquid water in oceans and rivers. Okay. Let us say how much amount of volcanic eruptions, just let us quantify how much volcanic eruptions must have happened, how many volcanic eruptions must have happened, and how much amount of water must have been brought into the hydrosphere. If you want to have a number, let us say, let us take volcanic eruptions over the past 100 years to be indicative of, let us count for the past 100 years how many volcanic eruptions have happened. If you take this to be an indicative of a century, let us say, let us extrapolate this number over the entire 4.5 billion years. Then if one volcanic eruption is able to release certain amount of, let us say certain amount of H2O, certain amount of water, then this X number of volcanic eruptions which happened over the period of 4.5 billion years must have released again a proportionate number of H2O, right. Now, if you put this proportionate number of H2O in comparison with the amount of H2O that is available in hydrosphere today, these two numbers should compare, or I mean they should have some relation, you understand. So, you take one volcanic eruption, if it is releasing a certain amount of water vapor, you take X number of volcanic eruptions which happened over the period of 4.5 billion years, and that must have brought in this much amount of water. Then you see that this, then you compare this number with the amount of hydrosphere that you have today. What you will realize is that the mass of existing hydrosphere is very, very small by 2 orders of magnitude. You see, the 2 orders of magnitude in comparison to what should have been present. That means there is a lot of water missing. So, where did all the water go? So, where did all the water, I mean, so you have a closed system. So, there is nothing which is escaping away from the earth system into the space except for hydrogen. There is nothing which is escaping the earth system, not the heavy elements, not the gas, nothing, right. So, in that case, where has all the water gone? I mean, 2 orders of magnitude we have smaller amount of hydrosphere. Okay. So, there are 2 theories here actually. There are 2 theories. One theory is that leakage from the hydrosphere. So, you have the oceans, and from the deep oceans, water must have leaked into the crust or into the core itself and into the inside of the earth along the seams of the crust. Is one theory. So, in order to account for the missing amount of water, one theory was that there can be a possibility that water must have leaked into the planet itself. The second theory is that water destroyed as a result of photodissociation by solar ultraviolet. Water, this lost water is actually nothing but that is destroyed as a result of photodissociation by solar ultraviolet radiation. Okay. Let us see what is solar ultraviolet. I mean, I have already said that in the beginning there was no oxygen, there was no free oxygen, so there is no possibility that there is no way that you can think about ozone. When ozone is not there, you have a free ultraviolet photons which are coming onto the earth. So, ultraviolet has the ability to dissociate water. Okay, this is another theory. So, if it is the case, then it is very easy to accept that now so far the processes which we have discussed so far, all the processes must have been the same for any other rocky planet. So, there is no reason for us to believe the processes must have been different, because they also came together from the rocks and they formed. So, volatile substance must have been trapped, of course, yes, and volcanic eruptions must have been there and they must have released a lot of water vapor. All these things must have been the same for Mars and Venus. So, it is very easy to accept that other rocky planets must have resulted in a very similar way. So, why is water absent on them? I mean, today we see water on this planet, but we do not see water on other planets, right. So, Mars, I mean, for example, Mars, the conditions are too cold to be able to sustain water in liquid form. That is true. There is ice on water, of course, there is ice on Mars, of course. And Venus, with the surface temperatures of nearly 700 Kelvin already, water cannot sustain in liquid form. So, it must have escaped. So, today I will stop with this. Now, we are at the point that we have to account for the missing amount of water, and for this missing amount of water we have theorized 2 theories. One is leakage across the seams, right. Another is photo dissociation. So, in the next lecture we will see how the missing amount of water can be accounted. So, we have to see if the water has actually leaked into the earth's crust along the seams, or we have to see if the photodissociation has a very important role to play to bring in free oxygen into the atmosphere. Okay. So, we will continue with the next class.